This work focuses on the Sierra Nevada mountain range, located in Spain. In this Mediterranean context, we have focused on the capability of Sentinel-1 SAR imagery to capture multi-seasonal wet snow dynamics, as well as introducing a hydrological approach to assess the connection between these wet snow dynamics and streamflow response. The main innovation of this work is the use of terrestrial photography in combination with Sentinel-1 SAR imagery and the use of Sentinel-1 SAR imagery to monitor the hydrological year. To explore the capability of Sentinel-1 SAR imagery to capture multi-seasonal wet snow dynamics over Mediterranean mountain regions, we have typically relied on the use of microwave techniques and more precisely the synthetic-aperture radar from Sentinel-1. To interpret the phases of snow melting, we have based our work on those that came before us. As such, we have defined the melting runoff onset, which is the moment when snow that has not yet melted begins to contribute water to the ground, and, therefore, to the basin. This phase can be detected through analyzing Sentinel-1 SAR images. It corresponds to minimum values in the time series of backscattering. One of the unique contributions of this work comes in our definition of melting cycles, for which we first studied the snow dynamics at a local and basin scale. Once the dynamics of snow cover were defined, the concept of a local minimum was incorporated, which allows us to confirm if within a period of snow melting, we experience contributions of snow cover to the basin. In this theoretical graph, we see 3 cycles in which we have a loss of snow cover and an increase in the number of pixels with local minima, thus confirming the contribution of snow to the system. A local scale analysis of the backscattering signal evolution at the Refugio Pokhara. The identification of different LMs allowed for an explanation of their evolution in relation to snowpack dynamics over Mediterranean mountain regions. Starting with the hypothesis that an LM triggers the onset of melting runoff and the 4 types of melting cycles identified by Pimentel et al. The local minimum type 1 is found at the end of a well-developed snowpack. It is representative of long-lasting snow cycles, with a large amount of snow, resulting from a long accumulation phase. The local minimum type 2 is not unique in the snow cycle. It describes a quick melting period that is stopped by another snowfall or cold period that refreezes snow. The local minimum type 3 is unique within the melting cycle, which means that before and after this LM there is no snow. In addition, it takes place at the beginning of the snow season, due to the energy exchange between the snowpack and the ground. And finally, the local minimum type 4 is singular. However, in this case, the minimum appears in sporadic snow cycles that occur during late winter or spring, and always after the main melting cycle. At the basin scale, we have obtained 2 kinds of results. 1. Separation of snow melting events based on the dynamics of snow cover, dry snow, wet snow, and the dynamics of local minima identified in each of the pixels, as can be seen in the figures A and B and C. 2. A map in which we represent, using colors, the date on which the local minimum is reached, and, therefore, we can see water inputs to the basin on a distributed scale. Once we understood the dynamics on a catchment scale, we were looking for a linear relationship between base flow and wet snow pixels. To do so, for each of the long-lasting melting cycles, we calculated a delay as the number of days between the date when the number of wet snow pixels was maximum and the date when maximum base flow was achieved. Finally, a linear connection between melting dynamics and streamflow was found for these long-lasting melting cycles, with a determination coefficient ranging from 0.62 to 0.83 and an average delay between the melting onset and streamflow peak of about 21 days. The results of this study have improved our understanding of snow dynamics in Mediterranean areas, and will also help to improve both water management and snowmelt forecasts and their impact on short-term flow.